Okay, folks, in the last video we learned about nuclear reactions. And today we'll just continue our whole radioactive radiation thing series talk. Okay, thinking of series, at the end of the last video, I had talked about what's called a decay series. So if uranium, okay, it's radioactive, we know that, it breaks down, forms something new by giving off some radiation. So that radiation that was given off, actually that U-238 radiation that was given off to form thorium and that helium atom, which is an alpha particle, there would also be gamma radiation. I didn't put that into the equation. I didn't put the gamma in. Gamma, sometimes you'll see it though. And so here was our U-238, and it ended up being thorium-234. Again, my goofy thorium-late. It's funny, thorium-late, goofy. And we have the helium. Sometimes you'll see this, not always, because it doesn't complete the mass on the left and mass on the right. It's not part of it, but sometimes you'll see this, and you'll see kind of that symbol there, which is the symbol for gamma. It's the Greek letter for gamma. It looks like a bird, I was drawing kids. I couldn't draw a bird. Still can't. So I draw birds, right? Like that. That's gamma. And gamma's given off. Gamma's always given off in this radioactive stuff. Nasty, nasty. Okay? So that would be the complete reaction. But the thing is, we know, as I was telling you at the end of the last video, that this is also radioactive. Thorium is radioactive. So it doesn't stop here. This will further break down. And eventually, thorium will become lead. Lead being relatively stable. But there are multiple steps along the way to get there. It doesn't just happen all at once. You can't go from here to there without going through here and several other steps along the way. That's called a decay series. So a decay series has multiple steps, 9 of them for this to take place. So some of the steps, you'll give off an alpha particle. Some steps will give off a beta particle. Okay, all right, so that's called the decay series. So we're just showing one step in the decay series of uranium to lead. Okay, so there are many steps. Most things, some things break down just once, and some things don't. Some things continue until they become a very stable form. Lead is stable. In order to get that stability, we need multiple steps to accomplish that, and that's our decay series. Okay, let's talk about Half-Life. Half-Life, back in the day, awesome video game. Half-Life, awesome. Half-Life, I bet you know something about Half-Life. I bet you do. I bet you do. Yes, you do. Now, Half-Life, okay, so I'll go back to the 238 and the uranium here. It breaks down, forms a thorium, gives off the alpha particle there. Well, how long does this take to happen? Okay, how long does it take to happen? Well, it depends. It's like those things I wear now because I'm old. It depends. Funny. It depends on what it is. Some things have a half-life of just like platoon. Some things have a half-life of, the platoon was pretty fast. We're talking like, less than a second they can have a half-life. Extremely heavy, massive things, in these particle accelerators that they create, these new atoms, these unnaturally occurring atoms that are produced above 92. Once you start getting into that's number 92, like atom 110 or whatever that one is, it's very unstable, breaks down very quickly. Some of them have half-lives of seconds, some of them have half-lives of days. Okay, some will have a half-life of weeks, some years, and some many years. Uranium, there are 2 different forms of uranium that are there's 3 different forms of uranium actually, but 2 that are relatively common. This is the most common form, uranium-238. It occurs like 93% of the time in nature. There's also uranium-235, and both of those have really big half-lives. One of them is in the millions of years, and one of them is in the billions of years. I always get them confused which one is which. You have to look it up again. I don't have everything in life memorized, kids, but I do know both of them are very, very long. Even the one that's a shorter half-life is in the millions of years. What does that mean? That means in a millions of years of now, I think it's like 5 million years if I remember correctly, then you're going to still have half of it left. That's what that means. Ooh, half-life. What does that mean? Half-life is the amount of time it takes for half of the radioactive material to decay, to break down, to change. So it's the amount of time. So it's a time number, the amount of time to break down to 1/2. All right, that's half-life. So if you have a radioactive material, so let's take an example of this. So no, with uranium, it's going to be around for a really long time, because if you have, let's say, 100-gram sample of uranium, and millions of years from now, whatever that half-life is, I'd have to look up specifically what it is. I think the place is 5 million years. 5 million years from now, you're still going to have half of it. You're still going to have 50 grams left. Whoa, that's a long time. Yeah, it is. We run into problems with that. We'll talk about that too later in the video. All right, so this means half-life, the amount of time it takes to break down to 1/2 the original sample. So let's just take the hypothetical situation. Let's say that we have 100 grams of this radioactive material, and the half-life is 8 days. Iodine-131, I do believe. I did some graduate work with that in graduate school. Iodine-131, its half-life is 8 days. It's a radioactive form of iodine. Iodine usually around 6 o'clock in the evening. Iodine, 6 o'clock. Funny. Okay, so let's say that we have 8 days goes by. Okay, 8 days goes by. How much of it would I have left? Well, I'd have 50 grams left, right? This is after 8 days. 8 days. Dazed and Confused, okay? A strange movie if you've ever seen it. Now, this one here, so, so you know what that means? That means this, right? So after 8 days, I have 50 grams. So after another 8 days, it'd be all gone. No. So you know that's not right. See, after 8 days more, I would have 25 grams. You keep cutting the sample in half. So after another 8 days, I'd have 12.5 grams. Then after another 8 days, I would keep going down, but I'm out of room, so I'm going around here. Stick with me. I'd have 6.25 grams. Ooh. And so on, and so on, and so on. I mean, really, it just keeps on cutting the sample in half. Cut it in half, cut it in half, cut it in half, cut it in half. The radioactive materials are on for a long time, even if there's a relatively short half-life, because you just keep cutting the sample in half. Now, eventually, you would actually break down to the point where you got 2 atoms left and 1 atom left, and at some point, that 1 atom will eventually just go boop and then convert and be all gone. But it takes a long time to happen. So to get down 1, 2, 3, 4, this would be 24 days from now, I could expect, all right, let's a little more than 6 grams of my radioactive sample. If this were like, for example, iodine-131, I would expect that many grams to be left after 24 days. So then sometimes half-life problems are that easy. That was an easy one, people. It was an easy one. Sometimes they are. Sometimes I'll say, or a problem might say, after 5 half-lives, how much material will you have left? That means you have to cut it in half 5 times. So cut it in half by 5 times, keep going in half, 25, so 12.5, 6.25, did I go 1, 12, 2, 25, 12.25, 6.25, 3.125 if it's half 5, 3.125 grams for my example here if I went through 5 half-lives. Okay, there's 1 half-life, 25 would be 2 half-lives. Okay, 12.5 is 3 half-lives, 6.25, 4 half-lives, 3.125, 5 half-lives. So after 5 half-lives, which would be 40 days, I'd expect to have around 3 grams left. Okay, so problems like that with half-life I hope aren't too difficult. But, life isn't always like that, right? You know it, it's physics, so why do you have to make things difficult? I'm not making it difficult. I mean, life can be difficult. We all know that. So there aren't all these easy examples to work with like that. Some are, but not all. Like, for example, if you have a half-life of 32 years and you want to know how much is going to be left when you have 14 days have gone by. Okay, if the half-life is 32 years, how much of the radioactive sample is left after 14 days? There's going to be a little bit of a problem there. We're not going to be able to kind of really work our way through that one just by cutting things in half. Doesn't work. Don't worry, we're physics. We got an equation for that. Okay, but for now, the whole idea of half-life is how long it takes that radioactive sample to break down to 1/2 of whatever the original sample was. Again, it can be years, it can be weeks, days, it can be seconds. Okay, it depends. And so we'll stop this with the half-life concept. This is the general half-life concept. We'll take this half-life concept and we'll apply it to more fun things. Fun, yes, fun, in the next video.